Now that you understand what the square law demodulator is, let's do some mathematical analysis of how we can use the square law demodulator or method to demodulate a signal or a modulated signal. As I explained in my previous video, for the square law, we pass our input, which is the modulated signal S of t, to a nonlinear device like we did for modulation. We pass the resulting output to a low-pass filter, and the resultant aspect is M of t. You have to take note that at the end of demodulation, it's either there will be a scale division of the amplitude of our message signal, or there will be some constants being multiplied to it. But at the end of the day, our message will not change. There can also be a phase shift, but it can also be compensated as well. So going straight to do the mathematical analysis for the square law demodulator, as I said, this is the block diagram. Now let's label the diagram here V1, V2, and then here the output. Let's take them one after the other. What is our X of t? During our modulation tutorial session, we were able to conclude that our modulated signal S of t is equal to AC into bracket 1 plus K M of t cos omega ct. Well, we're saying that our AC is the amplitude of our carrier wave signal, or our modulated carrier wave signal. The K is our modulation index, and the omega c is our modulated angular frequency. So this becomes our input. And we also establish the fact that our V2, the relationship that exists between the input and the output, which is the V1, of our nonlinear device is equal to A1 V1 plus A2 V1 squared. And therefore, substituting our V1, which is the input, this is the V1, and is equal to S of t, into this relationship, we are going to get our V2, which is equal to V out, to be equal to A1 being multiplied by this S of t, and so on. But remember that the A1 and the A2, they are both constants. In substituting whatever we want into this V2 or this V out equation, we are going to get AC into bracket 1 plus Km of t cos omega ct, then plus A2 into brackets AC bracket 1 plus K M of t all squared. Now let's look at what we can do over here. As I said here, the K is our amplitude deviation, or which sometimes we refer to as the modulation index. So let's try and simplify the right hand side first. Sorry, I didn't add cos. The cos, it's here, cos omega ct. Your part, so don't forget to add it. So we want to simplify whatever is inside here first, and when we do that, we are going to get into brackets AC plus K AC M of t, all multiplied by cos omega ct. So in doing this, we can further simplify them. Here's all squared. You can further simplify it as A squared into bracket AC cos omega ct plus K AC M of t cos omega ct, multiplying by AC cos omega ct plus KAC M of t cos omega ct. Now let's try and multiply them truth. So in doing this, we are going to get a2 out, ac squared cos squared omega ct plus ac squared k m of t cos squared omega ct, because I'm using this one to multiply this and this, and now I pick this, multiply this and this, then plus ac squared km of t cos squared omega ct plus the last one, this one and this one, will give us k squared ac squared and m squared of t cos squared omega ct. Now, in further simplifying it, we are going to get a2 ac squared cos squared omega ct plus a2 ac squared, or let's say this and this are the same, so I can say 2a2 ac squared k m of t cos squared omega ct plus k squared ac squared m squared of t cos omega ct. This is only the right hand side. Therefore, by adding the left hand side, the output of our nonlinear device is going to give us this one will multiply through this. We are going to get a1 ac cos omega ct plus a1 k m of t. Don't forget the cos has squared, cos omega ct. Now plus a whole of this. So this one will be here. So this becomes the output of our nonlinear device. In passing this output, a low pass filter, because we are done with the NLD, the nonlinear device. The next one is the low pass filter, and therefore we get our m of t. So in doing that, these are V out. In doing that, let's look at the equation here.
Has been altered from
this
m of t to m of
one
t
will go out to 0. And it is also having the carrier frequency, which is also higher frequency, it goes out. This is also having the carrier frequency, which is also a higher frequency. And aside that, there's no message signal inside. So even if we use trigonometric identities to expand it, we may get a constant, but that constant may not have the message signal that we are interested in, and therefore it also goes out. The next one also, the same thing applies to this one. There's no message inside of which we are interested of, so it goes out. For this, there's a message signal inside, but just that there's a carrier frequency, which is a higher frequency. The low pass filter will attenuate it or will block it from passing through. So that one also goes to 0. So at the end of the day, let's look at what is left. Now our V out becomes, which is our V2 becomes 2 of A2, as we have stated it over here. This is what is left. 2 of A2 AC squared K m of t cos squared omega ct. Someone may ask, why is it that this one there's a carrier frequency inside, which is a higher frequency, but the low pass filter didn't block it? Remember that there's a message signal inside, and if we use trigonometric identity to simplify it, we will get a constant of which that constant will also contain our message signal. That's what we want. We didn't take this one because they are all cos squared, of which we can use trigonometric identity to expand. We didn't take it because there's no message signal attached to it, of which when we do the expansion, you get a constant with the message signal that we are looking for. Therefore, the low pass filter will block it. So having this one, we can use the trigonometric identity cos squared theta equal to cos 2 theta plus 1 or over 2. This came from the fact that we have sine squared theta equal to 1 minus cos squared theta, of which, let me rewrite this one well. This came from sine squared theta plus cos squared theta equal to 1. And therefore, we can see that our cos 2 theta equal to cos squared theta minus sine squared theta. In doing substitution, we are going to get cos 2 theta to be equal to 2 cos square theta minus 1. And therefore, when we simplify it, that's what we are going to get. So having this one, we can substitute it back into this equation because they have this one here, where our theta equal to omega ct, or let's say omega t. And therefore, in doing that, we are going to get a2 ac squared k m of t multiplied by cos 2 times omega ct plus 1 all over 2. This is what we are going to get when we substitute it into this equation. And at the end of the day, let's rewrite them here. In doing simplification, we are going to get v2 equal to a2 ac squared km of t into bracket 1 over 2 plus 1 over 2 cos 2 omega ct bracket close. So when we expand this, we are going to get v2 equal to a2 ac squared km of t multiplied by 1 over 2 plus a2 ac squared km of t cos 2 omega ct. So this is the final equation. As you can see, the frequency of the right hand side has been even doubled. Thereby, when we pass it through the low pass filter, it will attenuate it. So this one also goes into 0. And therefore, our final result, v2 is going to be a2 ac squared km of t all over 2, where a2 ac squared over 2 is constant. And then our m of t is our message signal. So as I was saying earlier on, at the end of demodulation, there will be some scalar divisions, and this is the scalar division that I'm talking about, or I was talking about. And we have been able to extract our message signal from the modulated signal. So in summary, we passed through the modulated signal s of t through a nonlinear device, and then through a low pass filter, where it was able to attenuate all the unnecessary signals, leaving our m of t. And this is our m of t. So in my next tutorial, I'm going to use the switching method to show you how you can use it to demodulate a modulated signal. And thank you for watching. I'll see you in my next tutorial.